Change Initiative's webinar series. I just wanted to give you a couple of basic logistics here. If you have questions, please type them into the chat window and we'll be able to answer them. So here, I just typed questions here. So if you have questions, please type them into the chat window. We're wondering about who all of you are. So I am going to launch a little poll for you. And we'd love for you to just take a moment. You have about 60 seconds to fill this out. So where are you zooming in from and what background brings you to the meeting? So we'll give you less than a minute to complete this poll and we'll share the results so our speakers will have the opportunity to know who they're talking to today. And again, thank you for joining us on a particularly nutty day in the wide world of sports. We're really glad that you're taking an hour to talk forest carbon with us. Another 20 seconds or so. People are zooming in and filling out the poll very quickly, which is great. Another 10 seconds. 3, 2, 1, dink. Okay, I am going to share the results of the poll. So for all of you out there and for our speakers, most folks are zooming in from Maine, and a lot of folks are coming in from New England as well. We have a few from outside New England, and we have one Canadian. Thank you for zooming in with us. We have a good spread of folks that consider themselves foresters in a conservation-related field, scientists, and also folks in public policy, in forest industry, and a couple of interested public. So we're really glad to have you here, and hopefully this will help inform our discussion today. So I'm going to stop. Sorry, Jake said, please avoid using the word from here on out. Thank you, Jake. Noted. Okay, good point. So let's see. So again, if you have questions or comments like Jake had, please type them into the chat window. Aaron is going to get us started with formal introductions and launching us into the real meat of today's webinar. But just as an overview, we're going to hear from our first speaker, and you'll have time to ask some clarifying questions in the chat window, and we'll address those briefly. And then we'll hear from our second speaker, and then we'll have another brief time for clarifying questions. And we want to save a good chunk of time at the end for kind of facilitated Q&A and discussion on information that both presenters have shared. So we will definitely wind down before the top of the hour. If you have questions for our speakers, please type them into the chat window. If you have questions for me, you can send me a little private message and I can try to address your need. And I think with that, we're ready to get rolling. So Aaron, take it away.
All right, perfect. Thank you, Amanda, and thanks everybody for joining us today. Again, I just want to remind everyone that this is a series meant to happen, unfortunately, the first Wednesday of every month, which just puts us a little bit inconvenient today. But we had a really great turnout last month with Keith Daigneault talking about operations. Again, that's up online, and folks can basically go to the meeting page and view that. The same will be true today as we talk through the carbon budget, carbon management and credit. And next month is Sarah Nelson of the Appalachian Mountain Club and Jay Wason, University of Maine assistant professor, talking about changing winters. Obviously, we already have snow on the ground here in Maine, and that's somewhat unusual given timing and everything else. Again, this is a joint effort between the University of Maine Center for Research on Sustainable Forest and the Forest Steward Guild, and I appreciate Amanda for being here and helping with all of this. It's meant to be an interactive panel discussion. Both presenters today will give brief overviews, and then we'll try to keep this dialogue open and going. So I formally want to introduce both of today's speakers. Dr. Dane Hayes is Associate Professor of Remote Sensing and Geospatial Analysis. He's also the director of the Barbara Wheatland Geospatial Lab here at the University of Maine. In today's context, he's also been part of the State of the Carbon report at the national level and been involved with some global efforts as well. So Dan will present an overview of the carbon budget that we did for Maine a few months ago. And then Dr. Daigneault is Assistant Professor of Forest Policy, been here with us for the last 4 or 5 years, brings a nice international background from New Zealand as working with previously with the EPA. So it'll take more of a policy and in-depth dive to some of the components of our carbon budget. Again, I just want to point people that all of the resources for today's meeting are under the Forest Climate Change Initiative. From there, you should be able to scroll down and go into the State of the Maine's carbon budget, where we both have this detailed analysis. If you click on the picture, it should take you to the 2-pager, as well as if you want a more detailed access, we do have that all available. So with that, I'll turn it back over to Amanda and on to Dan.
All right, so our first speaker is Dr. Daniel Hayes. I think he will give you a more formal introduction as we get started, but we're excited to have Dan give us an overview of forest carbon, and we'll get a deeper dive with Adam in just a moment. So Dan, feel free to share your screen and take it away.
Okay, thank you, Amanda. Thanks, Aaron, for the introduction. That was plenty formal enough, so we don't need to do that anymore. But I am excited. I don't know who else is excited. I'm sure Jake is, because he's already in the chat box. But hopefully there's others of you that are excited to take a little tour, little Zoom adventure through the Maine's carbon budget. So I'm going to try to act as a bit of a tour guide. We're just going to jump in and check it out. But I am going to kind of roll through this just to give you an overview of what we've done and putting together some numbers and hopefully some new understanding of the carbon budgets for the state of Maine. So as I roll through it, maybe if you could just save your questions for and comments for after the presentation, you can always put things in the chat box and we'll discuss afterwards. All right. Okay, so we'll get started, presumably. Now, here's the problem that you have. Whenever you're stuck with a scientist talking to you about carbon budgets, they're going to start here. And this is a time series plot that shows the increasing concentration of carbon dioxide in the atmosphere as measured continuously from the top of a volcano in Hawaii. So it has been established as far back as the 1970s that the rapid increase in CO2 concentration is due to anthropogenic emissions from the burning of fossil fuels. And CO2, of course, is the major heat-trapping gas, greenhouse gas, responsible for the warming of the Earth's climate. And so while scientists try to project the range of possible future scenarios for future warming, policymakers might ask what actions we can take to curb these emissions, manage our carbon budgets, and mitigate the impacts of climate change. So this is where it gets interesting, though. This line shows the time averaged amount of CO2 emitted to the atmosphere from fossil fuel combustion over the past 6 decades, and this is global. This is what we refer to as the global CO2 source, the total emissions. But this line I just put on there now shows how much of all of that CO2 that's put into the atmosphere, this is the amount that actually remains there. So a lesser amount remains, and the difference between the two is what we refer to as the CO2 sink, between what's emitted and the growth rate of the CO2 in the atmosphere. So we want to ask what is responsible for offsetting or removing this substantial portion of anthropogenic CO2 emissions from the atmosphere. So the total source of carbon to the atmosphere is about 80% from fossil fuel emissions, with the other 20% from land use change, primarily due to tropical deforestation. The total source can be partitioned among its major sinks, or where those emissions end up going, in other words. The relatively well-known ocean sink shows a steady increase in total uptake as emissions have risen over the past 2 or 3 decades. As with the Mauna Loa observatory data, at any given time, we know with pretty good precision the total amount of CO2 in the atmosphere based on monitoring from mountaintops, airplanes, tall towers, and ocean vessels. The land sink, however, is much harder to measure or estimate directly, but rather we can infer it as the residual after accounting for the ocean and atmosphere sinks out of the total source. Now, this is highly variable from year to year, and over recent decades, the land sink is generally similar in quantity to the oceans, and it accounts for about 25 to 30% of the total source emissions. So in effect, the land and ocean act as brakes on the rate at which CO2 builds up in the atmosphere. While CO2 dissolves into the oceans at a steady pace currently and likely into the foreseeable future, the land sink is highly variable and subject to swings in the weather and other events like droughts, wildfires, and even volcanic eruptions. The critical question then is if and how this land sink will continue to operate into the future, or will it saturate or worse, even begin to flip in the face of all these other stressors? In order to predict the future sink with some level of confidence, we need to have good understanding of what controls it and how it operates. In this well-known study shown here, scientists compiled inventory statistics from around the world and found that nearly all of the sink on land can be accounted for within the Earth's forests. So you may be asking, hey Dan, well, we got a lot of forests in Maine, right? So what's going on there? What are they doing for our carbon budget? Well, that's a great question, and it's one that a group of us got together to try to figure out, or at least make our first best guess at, the state of Maine's carbon budget. We took a simple bookkeeping approach toward an initial estimate by collecting data on the carbon stocks of the major compartments in the budget. We then synthesized these data into a budget accounting for the flows of carbon among these various compartments in a series of what we might call our back of the envelope calculations. But before we dig into the numbers, again, we're talking science here, we need to build ourselves a conceptual model of the pools and fluxes of carbon within our system. In other words, let's organize our carbon budget so that we can plug in our numbers for the main compartments of carbon stock and the amounts transferred among them. First, we're going to look at the forest sector. Now, we all know trees take up huge amounts of atmospheric CO2 in the process of photosynthesis. A big portion of this carbon uptake is returned to the atmosphere through plant maintenance respiration, as well as decomposition as trees shed their leaves, drop their branches, and eventually die. The resulting net uptake is the small balance between these really large fluxes, and this carbon gained is then stored in live biomass, forest litter, and other dead material, and in soil organic matter. Importantly, in managed forests, live biomass can be removed in harvesting, and a portion of that carbon is transferred to the wood product pools. We can keep track of the fate of the carbon, whether it goes to the short-lived products like paper or longer-term storage in saw logs, for example. As the carbon in these wood products is burned or decays in landfills, carbon is released back to the atmosphere as CO2 and methane. Finally, some portion of the carbon in soils is transferred to the aquatic system where it dissolves and flows to rivers and lakes. All right, next let's look at the agricultural sector. While growing and consuming crops is often considered a zero-sum result in terms of the overall budget, carbon can be stored in or released from agricultural soils depending on tilling and other management practices. Livestock like cows, pigs, and sheep consume much of the crop biomass that is grown, and they contribute to the net source of agricultural carbon, a large part of which is methane emissions. In urban areas, they typically act as a net sink with carbon taken up and stored in trees, shrubs, and grasses. Urban areas are expanding in most places, albeit not as rapidly as in Maine as in other parts of the country. Wetland plants take up carbon very slowly, but can store it for long periods in their cold, saturated soils. There is a net loss of wetland carbon in the budget when they are drained and converted to other land uses like agriculture in urban areas. Now, as with forest soils, dissolved carbon from these other land uses is transferred to the inland water system. The aquatic carbon that is not stored in sediments is either released back to the atmosphere as CO2 and methane outgassing, or it is exported to the ocean. In coastal ecosystems, carbon is accumulated as sediment and in the biomass of eelgrass and salt marsh vegetation, for example. Okay, now that we know where the carbon is stored and how it moves through our system, let's collect some data and start plugging the numbers into our budget. A summary of our basic stock data is shown here. This table shows that the vast majority of the carbon stored in Maine lands is in forests, with lesser amounts among urban areas, wetlands, and agricultural soils. While coastal ecosystems represent a small amount of the overall area of our budget, they do store carbon at a relatively high density. In all, Maine's land base stores more than 2 billion tons of carbon across the various sectors in their compartments. So great, now let's see if we can track how all of this carbon moves into, out of, and among the various components of our budget. Let's start by plugging in the numbers into our boxes and arrows and calculate what that does to the atmospheric sources and land sinks in Maine. All right, now I don't mean to alarm anyone, but I should warn you that there's going to be some arithmetic involved. So hopefully everybody's okay with doing a little bit of math here. First, let's start with the fossil fuel emissions. The U.S. Energy Information Administration reports annual estimate of fossil fuel emissions by energy consuming sector in each state. Based on industry reporting and tracking things like consumption data and sales receipts, the quantities of fossil fuel emissions are fairly well known. In effect, it is the largest flux quantity in our budget, but it's also the least uncertain estimate. Plotting these emissions estimates for Maine since 1990 shows that fossil fuel emissions peaked in the 2002 to 2004 timeframe, primarily due to a decline since then across the electric, industrial, and residential sources. Meanwhile, emissions from transportation have remained steady and now account for over half of all emissions in the state. We can gather up the emissions data from all of these sources of fossil fuel combustion, here shown as the quantity of carbon subtracted from the fossil fuel pool by fuel combustion. Let's note here that we'll be showing estimates of stock change within each component and the fluxes between them in thousands of metric tons of carbon per year, averaged approximately over the 2006 to 2016 time frame. When we sum all of these fossil fuel sources, we estimate that Maine has on average emitted nearly 5 million metric tons of carbon in each year over the past decade or so. We'll add that source quantity to our atmospheric pool. While we're adding sources to the atmospheric pool, let's also consider the net emissions from the agricultural sector, which we estimate to be about 228,000 tons of carbon per year from 2006 to 2016. We'll send that to our atmosphere pool, and now we've got a total source of 5,125,000 tons of carbon added per year on average over this time period. Did you see that up there at the top? Hopefully everybody did. We're keeping track of our budget, and that math isn't so bad, right? So we can keep going. Everybody good? All right. Let's now see what happens to the carbon in our atmosphere pool as we account for the carbon added to our sink compartments and how these might offset some portion of the original emission source. First, carbon stocks in forest and wood product pools are estimated by the U.S. Forest Service, which measures this nationwide inventory plot network on a 5 to 10 year cycle. We can compare two inventories and calculate the total change in carbon between those two time periods. The change accounts for all processes, including growth, mortality, decay, disturbance, and harvest removal. These estimates suggest that Maine forests gained nearly 3 million metric tons of carbon per year, primarily in its live biomass. We'll add those to our forest box in our budget, while also noting that the 2,675,000 tons of carbon per year accumulated in live biomass is the quantity that is left after the amount that is removed in forest harvest. The inventory data show that on average, 3,780,000 tons of carbon were harvested per year and accumulated in the wood products pool in pulp and paper, sawlogs, and landfills. Based on the life cycles of these different products, we estimate that about 3 million tons of carbon per year was returned to the atmosphere from wood decay. Adding this to our atmosphere pool, we're now up to an annual source of over 8 million tons of carbon per year. But we still need to include the net uptake of the atmospheric carbon by the forests. To calculate this estimate, though, we also need to account for the carbon exported from forest soils to the aquatic system, which we estimate to be about 431,000 tons per year. So now we can finally add up all of the stock gains in and transfers out of the forest carbon pool to infer a net uptake of more than 7 million tons on an annual basis. Drawing this down out of our atmospheric pool then, coincidentally, now puts our net source estimate at exactly 1 million tons of carbon per year after accounting for forest uptake. Whew, that's a lot of math. Who knew science was going to be so strenuous? But all right, stay with me. We're almost done here. Let's just fill out our budget with a few more important compartments and fluxes. The stock changes and fluxes in these other land covers are estimated locally with inventories or research projects in representative sample areas. These estimates can then be extrapolated using remote sensing and its derived math products, such as the USGS National Land Cover Dataset. We estimate a small reduction in wetland carbon stocks as these have decreased in area coverage across Maine between 2006 and 2016. Statistics for urban areas suggest carbon gains in both vegetation and the soils. Just like our forest analysis, we need to account for the carbon that was originally taken up in these other land covers, but then exported as dissolved carbon to the inland water system. These estimates are based on the large network of river gauges maintained throughout the country by the U.S. Geological Survey. Of this total carbon export, about 92,000 metric tons are buried annually in the sediments of inland water bodies. Measurements of dissolved carbon at the mouth of Maine's rivers suggest that about 267,000 tons of carbon per year, originally from land, is exported to the coastal ocean. Coastal ecosystems also show a net gain in carbon stocks of almost 90,000 tons per year between 2006 and 2016. Okay, now that we have all of our boxes filled in and the arrows between them figured out, we can finish up our budget by calculating the remaining vertical fluxes, i.e. the net impact of these various sources and sinks on our atmospheric carbon pool. Adding up the stock change in aquatic export for the wetlands suggests an average annual net uptake of 55,000 metric tons of carbon over the 2006 to 2016 time period, bringing our atmospheric carbon source down even further to 945,000 tons per year. Urban areas in Maine take up an additional 122,000 tons of carbon from the atmosphere annually, putting us now at a source of 833,000 tons. Finally, we can balance out our budget by accounting for the source of carbon as a result of outgassing from the water column in inland and coastal waters. This adds an additional 290,000 tons of carbon per year to our atmosphere, bringing our final estimate for the average annual net carbon source in the state of Maine to 1,203,000 tons. So there you go, everybody. Nice job. But now, after we pat ourselves on the back for putting this all together, I want to just sit back and reflect on this for a minute. In other words, what does this all mean? Let's go back to our original estimate for average fossil fuel emissions from Maine's energy consuming sectors, highlighted there on the left. Taking the balance of net uptake in forests and net release from the decay of wood products, we get an average of 4,125,000 tons of carbon per year sequestered in Maine's forestry sector. This represents a 75% offset of its 4,897,000 tons of fossil fuel carbon emissions each year. Considering the net balance of the other land sectors, our budget shows a net 78% offset on fossil fuel emissions. But then adding back in the inland and coastal water sources, we arrive at a total sink offsetting 75% of the state's fossil fuel emissions over the approximate 10-year period around 2000 to 2016. As with the global study we saw earlier, it appears that is also generally the case in Maine, where the forest sector accounts for basically the entirety of the land sink. So overall, this budget shows that of the nearly 5 million tons of annual carbon emissions in Maine, a little over 1 million, or about 25%, actually remains in the atmosphere after drawdown in Maine's lands and rivers. So we can simplify the budget and visualize the contributions of the various major components. The forest sector, including forest growth and wood product storage, is by far the major contributor to the overall budget, offsetting 75% of fossil fuel emissions and accounting for nearly all of the land sink. We've summarized these key findings on the Maine Carbon Budget Fact Sheet distributed by the Center for Research on Sustainable Forests at the University of Maine. Now that we have a first-order estimate of the state of Maine's carbon budget, we can now begin the work of filling in the data gaps and reducing the uncertainties in our estimates by adding new, more highly resolved information at greater precision. Carbon is estimated from ground-based inventories, flux measurements, remote sensing observations, and mechanistic models. The goal is to advance our research and stakeholder applications toward a reliable and accurate framework for carbon monitoring, reporting, and verification across Maine's forest sector. In Maine, carbon is measured at NOAA Tall Tower in Argyll and at the Howland Research Forest, pictured here, which is home to the second longest running ecosystem flux monitoring site in the world. Our collaborative group of research and investigators here at UMaine is pursuing this goal through several projects with various sponsors and partners, including NASA, the National Science Foundation, and the Cooperative Forestry Research Unit. Through this research, we are building an improved diagnosis of our carbon resources, improved understanding and attribution of the changes in the carbon cycle to their causes and consequences, and making advances in predictive capabilities that provide information for decision-making based on various scenarios of forest conditions in an uncertain future. Okay, so that's the end of our quick tour around Maine's carbon budget. I very much appreciate your interest and attention to this little adventure, and I look forward to the discussion that follows. So thanks, everyone.
Thank you, Dan. Apologies for people who were hoping to not do math today. We have another couple of questions for you. I'm not going to say the P word. So first, we're wondering, did you find the pre-meeting materials useful as an intro to today's discussion? And it's an anonymous poll, so it's okay if you can be honest. And we're also wondering, kind of based on the pre-reading and what Dan just shared, what was the most important takeaway for you? So while you're filling out this couple of questions, if there are any questions that you want that you have for Dan, we'd love to hear them at this time. So please type them into the chat window. Let's see. Yeah, so Dan, I think he answered Jake's question. He was kind of wondering about the role of soil carbon in the forest accounting. Do you want to just clarify that real quick while folks are filling out the poll?
Sure. So I don't know if I see the exact question, but the forest number does include live, dead, and soil. Yep. So these are all, in theory, part of the FIA inventory that are measured their stocks in a 5 to 10 year period. So we can take the difference between those pools. The big caveat, there's caveats on all this stuff. You know, it always, when you get down to the devil's in the details. The soil is probably the least, in my opinion, and not just my opinion, it's probably the least well-represented number in the forest carbon budget, because it's not measured with quite the intensity that the other measurements are made, and so it's a little difficult to draw some real inferences from the soil carbon numbers that we get from FIA. But yes, that is part of the whole system. So
great, thank you. I'm not seeing other questions come in, and since we do have another speaker, I'm going to end this couple of questions. Oh, actually, I'll end our couple of questions. And Jake had another question: how confident are we that the soil and dead biomass, though, are essentially static? So that's another question. I don't know if Adam's going to get to that, but we'll let Dan take a stab, and I will share the poll in a moment.
Yeah, don't listen to Adam's answer. That's not good. Yeah, so the dead, I think the dead biomass is you know, that's an important term, because what that really reflects is the kind of balance between growth and mortality, particularly through disturbances. So so you see a situation in Canada, for example, that they have they're a small nationwide, they're a small but fairly steady carbon sink in their forests, but they have so much disturbances and fire and mountain pine beetle outbreaks and all these other things, that a lot of the carbon is actually stored in the dead or material after disturbance before it decays. And so that's actually a really large portion of their overall budget. So it's a very important term, especially where you're in more northern forests where you have slower growing conditions, but more disturbances.
Great, thank you. All right, thank you, Dan. Virtual applause, and we will be coming back to you for questions. Adam, it'd be great if you can queue up your presentation, and while you're queuing it up, I just want to remind folks that Aaron is sharing some really helpful links in the chat window. And just a brief response to the couple of questions that we shared. It turns out that 66% of you were thinking about something else and didn't have a chance to do the pre-reading. I don't know what you were thinking, but anyhow. And then more importantly, based on the carbon budget review, the biggest takeaway was the high positive contribution of forests and wood products. So thanks for sharing that. And Adam, hopefully you can get queued up and we'll get rocking and rolling. Again, please type your questions into the chat window and we'll address them. We'll address them as soon as Adam is done. Thanks. And Adam, you're still on mute. Maybe that was intentional, but just checking.
Yeah, can we at least see some slides?
We can see the slides and we hear you now.
Okay, great. No, that was intent because I was just trying to figure out. All right, so a couple of different things that I'm going to go over. Actually, three things Aaron sort of teed up that I'm jack of all trades. So I'm going to quickly try to go through a few different aspects, building up of what Dan sort of talked about. The first thing is just looking at, this was I think a short video that you were asked to look at, some of you, and that was basically looking at how Maine's greenhouse gas emissions stack up. All right, so, you know, basically Dan showed you the budget for Maine. A lot of times what you see or you hear is that globally, global ag and forest contribute to net positive 24% of the total greenhouse gas emissions. So the sort of land use change, forestry and agriculture sectors are net emitter. If you go to the US EPA, they estimate emissions every year in sequestration and find that forests roughly basically remove about 11% of our gross emissions from the atmosphere, or sorry, gross emissions coming from the US year on year. And in Maine, depending on what study you look at, Dan talked about basically our net land sink is removing roughly about 79% of gross greenhouse gas emissions, depending on what year you look or whatever, and what calculation you use, it's somewhere along the lines of sort of 70 to 75%, right? So it's basically noting that basically these types of carbon budgets that you do and approaches to accounting can result in vastly different results. So to understand this, what we really need to do is also look at how emissions in Maine have gone over time. So green line is the gross greenhouse gas emissions. So that's from primarily from fossil fuels. The red, which is below the x-axis, is the amount of sequestration year on year that's being basically additional sequestration that's occurring in our forests, but in this case, not necessarily the harvested wood products. And basically the lower that this is below the x-axis means the more that's being removed year on year. And what that means is that Maine's forests are basically the rate of growth is faster than the rate of removals. And if you can take the green line minus the red line, we get net greenhouse gases, and that's basically estimating what gross greenhouse gases less this removals may be in terms of, and roughly Maine is around 5 million metric tons carbon dioxide per year, which is basically equivalent of saying, at least if you look at this sort of assessment that we're looking at, a little over 70% of forests are removing a little over 70% of Maine's gross greenhouse gas emissions. We got us curious going sort of like, where does Maine stand relative to the rest of the country? So what you can do is you can look at EPA as a good data source on fossil-based emissions, and the Forest Service has annual sequestration of just, again, standing forests, not in the harvested wood products. You look at that, Maine overall is one of the lower emitting states, as we expect from a fossil-based perspective. It's sort of 20th in rank in terms of forest carbon sequestration. Interesting enough, Mississippi is #1, right? So with all that plantation forest, that sort of the age and structure of that forest is sequestering a lot year on year. Whereas Maine's not nearly, it's still quite good, but it's sort of limitation in terms of fast growing species and stuff means, you know, and just terms of actual like breadth of geography is limited there. And we can take this slide and this slide, put them together and find out what are net greenhouse gas emissions by state. Right. In this case, basically, you want to have a lower number. It means you basically have lower net greenhouse gas emissions. And Maine is 48th out of 50, with Oregon being 50. All right. And so what that means is basically, you know, comparison. We're basically our abundance of forests are allowing us to basically remove a high proportion of greenhouse gas emissions. If you want to then look at percent greenhouse gas removal by state and rank them, so this isn't just the net emissions, but now we're looking at the proportion of removals that each state is doing relative to their fossil fuels. Maine ranks 4th, just behind, I believe it's Mississippi and Oregon and Vermont. And so collectively, you can sort of just look at sort of how these different states rank in terms of percent of actual removal. And so we said, you know, Maine is somewhere in the lines of 70 to 80%, depending on how you do that calculation. It's just Mississippi, Vermont, and Oregon. Their forests are removing more than Maine in terms of proportion of greenhouse gas emissions. And this is all suggesting that year on year, again, growth is basically growth on the stand is greater than the amount of carbon that's being removed through harvest and or sort of decay happening naturally. And then so the other states on the other end that you would expect that are having a lot more removal compared to growth are from a proportion standpoint are the areas basically with not an abundance of forest, or those in the sort of the Rocky Mountains that face a lot of threats over the last few years of sort of pests and fire as well, which are leading to sort of relatively large carbon removals. So with that, you can use that to sort of establish like, okay, well, what's the role of forests in all this? Why are we concerned so much about the sort of the carbon budget and sort of the relative contribution of forests to you know, removal of greenhouse gas emissions? Well, this all has to do with sort of policy that are trying to influence sort of how different states or countries can meet their sort of climate change mitigation targets, of which a big one that people have been proposing over time has been the use of forest offsets, or basically, you know, incentives to encourage the faster and more abundant growth of forests to help offset some of those greenhouse gas emissions. For context, Maine doesn't have a formal policy that says exactly that, you know, forests are going to contribute this much, or from that perspective, but the governor's office and the legislature have established that by 2050, gross greenhouse gas emissions should be reduced by 80%, and by 2045, Maine should be net zero, which means basically gross greenhouse gas emissions coupled with additional removals from in terms of sequestration on soils and forests should be net zero. So that's sort of establishing an understanding that there could potentially be policies put in place soon to help deal with that. So what's the role of forests in greenhouse gas policy and carbon markets? So as we sort of indicated, even here in the States and looking at the different states, but really this is the thing globally, it's really this idea that forests can be a large contributor to climate change mitigation. Or on the flip side, if there's no incentives to sort of keep forests as forests, you can see there's a lot of emissions that can happen as a result of deforestation. And the mitigation potential really varies with geography, carbon price, the options, et cetera, that people can put in place. a lot of international climate policy proposals are really highly dependent on some sort of forest-based mitigation or sort of land-based mitigation to minimize costs. And actually only New Zealand, where I worked before I came here, includes the forest sector specifically as actual mandatory coverage in their emissions trading scheme. So they're the only country in the world where if you have forests that were planted before 1990 and you cut down that forest, you actually have to pay essentially a tax or a penalty for cutting that and converting to something else. If you replant the forest, you don't have to pay anything. But what it's attempting to do is recognizing that forests provide a large carbon sink, and if you sort of change your land use, that there's could be a penalty associated with it. Everyone else, it's basically you can volunteer to basically get credits put on your land, and then you can volunteer basically of which market you'd like to be a part of. But it's not mandatory that there's any sort of limitations on the type of land management that you can do associated with carbon. So how does the market work? We've sort of probably all seen something like this before, but the idea is generally, the state or some sort of national entity puts a cap on greenhouse gas emissions, and there might be two factories that have to face this, basically this red dotted line in terms of the amount of emissions. As a result, one might have excess emissions, all right, and so they can do sort of three things. One is they can basically reduce their emissions by implementing technology on their own, in their own sort of factory. They can then actually pay another factory to reduce their own greenhouse gas emissions and sort of trade with the two entities. All right, so they can purchase credits from the other factory who's also basically been allotted a certain amount of units, but knows how to go above and beyond that to potentially sell into a market. All right, or forest and agriculture entities can basically create offset credits that then enter into the market, that then basically allow this market to be larger. Therefore, emitter A can choose sort of where they want to purchase the credits from, where obviously you're going to choose whatever the lowest cost option may be. The idea is to increase economic, basically reduce costs by having more people participate in these markets. As I sort of indicated, really including incentives for forest carbon sequestration is shown to have a lot of benefits. It potentially, in some studies, have found that it can reduce the cost by up to 40 to 50% compared to some policies that don't include forestry. And in the US, there's really been sort of modeling has indicated that there's a lot of low-cost land-based greenhouse gas abatement, and a lot of that is expected to come from improved forest management. Basically, that's really what we're looking for in the case of Maine. There's not really the potential to expand our forest that much. So what we need to do is come up with the ways in terms of what they call improved forest management, but a way to increase carbon and biomass yields in our existing forest through changes in silviculture and broad management. Just a couple notes on carbon credits. So there's really, it sounds great in theoretical terms, but the markets are still relatively nascent and haven't become as ubiquitous as some might have thought when they sort of came up with this sort of 15, 20 years ago. The first question is, are credits being issued for real gains in carbon? So this is the question about additionality, permanence, and leakage. So are you actually really, when you're buying that credit, is that truly an additional credit above and beyond what a landowner was going to do? Are mechanisms put in place to ensure that it's permanent, right? We're living in natural systems. And just because you're not harvesting a tree in Maine, does that mean that some other, the market isn't just going to go and cut down an additional tree in South Carolina to make up for that? Right. And if that's the case, then there's an issue with what we call leakage, because basically you're locking up carbon here, but that might just be releasing carbon from a harvest somewhere else. There's also voluntary versus regulatory markets. So really the question here is, how flexible do you want to be? So if you enter regulatory markets, some of them basically have a 100-year commitment, right? Whereas voluntary markets sort of vary in the sort of level of stringency. But with that, credits are generally valued a lot higher on regulatory markets than voluntary markets. So there's a trade-off there, but there's also a benefit. Another aspect that people raise a lot is this concern with transaction costs. So, a lot of projects can cost $100,000 plus to sort of set up and basically get your forest sort of approved for the sort of sale and transfer of credits. And so really you likely need thousands of acres to truly be viable. And there's questions there, particularly of if you have a lot of sort of small woodlot owners, who might think that they could benefit from this. The question is whether or not there's sort of limitations to entering into the market because of these transaction costs for the auditing of your land to become basically credible for the project development. The third aspect that I'm going to quickly touch upon and build a bit more about what Dan talked about in his carbon budget, because I've been asked this question by quite a lot of folks, has to do with how do you estimate carbon in Maine's harvested wood products, and why is that basically you know, of the amount of removals that sort of get removed in terms of sort of harvest, why is that such a high proportion of that is actually being considered what we call decay? Why is that going back into the atmosphere, not being stored in other, basically stored in products? And so I'm going to go through sort of the accounting that we go through to come up with that numbers to illustrate that a bit more. So to understand sort of where are wood products, we need to understand what this wood product cycle is. So you start with a tree in a forest, you harvest and remove it from the forest, right? And that basically then becomes industrial roundwood. All right, that roundwood can then get deposited, processed at a mill, of which then it gets turned into lumber, panels, or paper. All right, and then that can basically turn into, you know, that's used in terms of manufacturing and construction that become end-use products. And all along the way, these different stages basically become, you know, deposited through either it's emitted, right? So it might be burned, might be totally discarded and decayed, or it's thrown into a landfill, which basically where it can continue to store the carbon in the landfill. But there's these sort of aspects of the cycle that all along that sort of this cycle or supply chain, there's opportunities for emissions to occur. On top of that, you know, you can say, well, we're going to make some end-use products like houses and furniture, right, or paper. Well, each of them also has sort of basically a decay associated with their product. So things like single-family homes, all right, have like a sort of, if you think about it in sort of carbon decay or sort of half-life, right? Their half-life is quite long, all right, because, you know, the turnover of homes don't get destroyed or sort of burned or anything like that, right? So the half-life is quite long. On the other end, sort of half-life of paper is like 2 to 3 years, right? So that quickly basically sort of gets taken out of the sort of product stream as a result, right? So you need to understand sort of what's the distribution of products that are being made in the state that can lead to sort of these different rates of decay. The next thing you can do is sort of take that aspect, all right, the notion that we know that basically when you harvest something, right, when you do that, convert that into an actual product, there's lots of loss along the way, all right, that comes in the form of decay. Some of that might end up in a landfill, which we can consider sort of storage, right? But actually, if you look at some of the actual numbers that come out of the Forest Service and the IPCC's sort of accounting numbers, we can have that if you start with a sort of just a full tree and you remove it, even in year 0, upwards of something like 40% is actually emitted through sort of combustion of energy or emitted totally without energy, right? And so this is the yellow is basically just sort of total waste. At least if you're producing for energy, you're sort of offsetting the use of an alternative form of energy, of which some may be fossil-based, all right? And then so on the left-hand side, well, this is all about saw logs, but you can see the saw log decay function, even if roughly sort of 59% of what you harvest starts off as a saw log, right? Over time, sort of because of where the product end use might lie, right? There's a good proportion that basically gets transferred and put in a landfill, and additional that get basically decay through energy or non-energy. On the pulp log, we can see what we would expect is that the decay rate of harvested wood products become a lot higher. And so as a result, you get that sort of after 20 years, less than 10%, well, I guess if you add the landfill, but less than around 10% is actually still in use. With landfills, we maybe get up to 25% of what was harvested in year 0 is actually basically stored in some sort of product. All right, so such that basically over 100 years, maybe roughly 15% of all carbon that was in pulp logs are actually still sort of stored somewhere and haven't been decayed out to the atmosphere. So that's roughly how we can put that together to get to our 20 to 25% rate. Also, we got to acknowledge that even across basically hardwoods and softwoods, there's different levels of decay, again, based on sort of the distribution of end use. So we have to recognize that. Particularly softwood pulpwood has a much steeper decay curve than hardwood pulpwood. In terms of products, saw logs, they're pretty similar. So what we can do is we can put this all together to then understand how sort of collectively sort of Maine's harvested wood product carbon might look over time. If you can think, you talk about sort of removals are up here, and then there's some immediate decay, and then that sort of happens over time. You can look at on average over 100 years, the amount that's actually being stored in the four different products: hardwood pulp, softwood pulp, hardwood saw, softwood saw together. Basically, it's averaging around 850,000 tons of carbon, which is relatively close to that number I think that Dan put up if you sort of do the arithmetic. And so to understand that, because it basically means on average about 32%, in this case, the way I've done it based on, I think I looked at 2016 numbers, maybe you could get upwards of 32% being basically stored on average in any given year. Recognizing that even this year, we might have harvested some products and we're basically having a number that's high, so relatively high. We also have to account for products that were harvested 50 years ago, right? And are basically leaving the sort of different aspects or transitioning different aspects of the carbon cycle as well, of the harvested wood product cycle as well, which can also have an influence. This figure is just, again, another way to articulate sort of where the flow of harvested wood products are happening sort of in terms of a 100-year average, right? So you have saw logs and pulp logs that come out of the harvest, all right? There's also biomass and stuff that comes out of the harvest, but that's sort of immediately combusted, right? And so then you have the proportion that can go into long-lasting pulp and saw log products, an amount that goes into landfill, but a lot of this is decay and energy, right? So a lot of Maine's wood is going into that. So that made me ask the question, what if we shift all the harvest in 2016 just to saw logs? So it's just a very hypothetical, but if somehow you took the 2016 harvest and we basically said, instead of having any pulpwood at all, somehow we removed the same amount of tons, but we all just removed saw logs. All right, so the removals from the forest are the same, but the products they're going into is slightly different. You roughly can estimate that you're going to maybe increase overall sort of carbon storage in harvested wood products roughly by 15%, but that's it. So it suggests that although it might be a climate strategy to shift into more long-lasting wood products, just the way that sort of at least historically these products have decayed over time, all right, it's not necessarily going to mean that it's going to be a super quick sort of fast solution for Maine from that perspective. I think I'm going to leave it to that. I'm sure I had plenty of things that sort of piqued people's interest, and happy to discuss more and get more insights from the audience. So thank you for that.
Thank you, Adam. All right. Well, I have another couple of set of questions to share with you. So I hope you were paying attention. And while you're filling out this one question, we did have a couple of good questions that came into the chat window. So just rewinding a little bit, we had a question: does a drought year like this summer with huge solar radiation versus average result in significantly higher photosynthesis than might otherwise be expected and thus mess with the models? Adam?
That's not for me. I'm not. Yeah, that's a Dan question.
Or even a Jay question, but yeah, we'll get Jay in another webinar. I don't know, Dan, do you have a response?
As soon as I can unmute, I just want to make sure that I was trying to read through the comments, and you're talking about the one from ML, maybe drought year.
Yes.
Okay, drought year like this with a huge solar radiation. Okay, that's so the perfect scientist answer is, well, it depends, and it's actually probably not. I wouldn't say that you'd have higher photosynthesis. The simple thought, and mechanistically speaking, that photosynthesis is going to depend on three things: the amount of solar radiation that you mentioned, the temperature, as well as the water availability in the soil. And so the water availability, it's sort of a playoff, and it depends on species and all different traits and things. So you'd have to kind of look at it closer, which one of those sort of wins out. But typically, drought has a decreasing impact on photosynthesis, while at the same time maybe or maybe not if impacting the decomposition flux too, that balances everything out. So the net of it is, for most of the studies, it really varies by biome, but globally speaking, drought typically has it can be a little bit of a lag effect, but drought typically has a net source effect on forest ecosystems. It results in a release of carbon.
Interesting, thank you. And again, please put your questions into the chat window and we'll be sure to address them. We had a question that I think will go to Adam from Ali Kosiba in Vermont. She says, there are a number of forest carbon offset projects in Maine. Did you subtract those ERTs from the overall Maine carbon budget?
No, we did not. So this is this interesting sort of discussion that we've had with many about what is a carbon budget versus what is sort of Maine state like greenhouse gas policy budget. And so you can sort of get into the accounting questions across, and there's a spectrum of what's included in one versus the other. So the way we've done this is we basically, and Dan, correct me if I'm wrong, but we basically just said, here's the boundary of Maine, the geographical boundary of Maine, and we're going to just basically account for everything we can within that boundary, not worrying about whether something is already getting carbon credits for somewhere. Related to that, the question that we're continuing to wrestle with is, Maine produces more harvested wood products than we consume, which means we're actually exporting some of that stored wood somewhere else, right? And so then there's another question about how to deal with that. And so the IPCC and others sort of have different levels of accounting that you can do to think about that. But that's be another case where we're potentially overestimating the sort of potential that Maine might have from a policy standpoint, but not necessarily from a pure carbon budget standpoint.
Got it, thank you. I have a quick comment. So on one of your last slides, Adam, it looked like the decaying wood over a 100-year time period would take up a significant amount of where, of just kind of carbon hanging out there until it's lost to the atmosphere eventually. But instead of, it says no value or something like that, I think was the phrasing on the slide. I just want to comment that I think from a wildlife perspective, I know we have a couple of wildlife biologists on this webinar. They might disagree with that that phrasing because it does provide additional value, and that's part of why we have this series, because we are going to be addressing wildlife issues in a future webinar. So might have no monetary value, or I don't know what it would do for carbon value, but there is wildlife value. I didn't mean to dish on you, Adam.
No. So I want to be clear though, because this is where people get confused by what we mean by decay in carbon accounting, right? It doesn't mean necessarily that these are residues on the forest floor. These means that something was harvested and like physically removed from the stand, and it's somewhere, but it was not used for energy, and we can't find it in products. So that's what I mean by it has new value, because it's actually, it wasn't utilized for any sort of, as far as we know, the way the accounting goes, it wasn't utilized for any product. So exactly where it's happening, it's decaying, like literally decaying somewhere on some shop floor or something. It's hard to figure that out, but it's not any sort of coarse woody debris or anything in the forest. That's already accounted for before we talk about removals.
That's really important. Thank you for clarifying that, because I was definitely imagining, like down tops or something from a typical harvest. Yeah, but thinking that it could be mill slabs or left somewhere, that just seemed like a really high proportion decaying in an unknown space. So thank you very much for clarifying that, Adam. I am going to keep an eye out for additional questions, but in the meantime, I'm going to end this one question and share the results. So we'll see how Adam did in teaching us about forest carbon. So as people were thinking about takeaways, most important policy implications of the carbon budget, most people took away maintaining the working forest and support the use of wood products. Folks also took away the first item, reducing the overall emissions with a focus on renewable energy. Also thinking about minimizing land conversion and general impacts on natural ecosystems. People also recognize the need to develop innovative carbon markets that support beneficial practices. And nobody said that we should just do nothing. So on the day that the United States of America is withdrawing from the Paris Climate Agreement, I think that kind of underscores the case that we here in Maine have an opportunity and a responsibility to manage our forests and other natural resources with carbon in mind. I know we have just a couple minutes left. Aaron, did you want to get a word in edgewise before we get to the wrap up?
No, I think this has been a good discussion, and I appreciate both Adam and Dan for presenting this. As Amanda indicated, that we'll be sending out these materials as well. I did want to highlight that in the soils question, we actually used the NRCS estimates, which is in the paper that I shared, and not the FIA estimates. and the soil carbon budget for Maine.
Great. Thank you for clarifying. So we
All
do have,
future questions on soil are going to go to Ivan, though. There's a lot of dirty laundry going on there that I didn't want to.
Right. But my question with that, Aaron, is that is there any actual flux in the soil in those estimates on a year-on-year basis? And my understanding is that there's not.
You're correct, Adam.
Okay, so I attribute it to the wrong source, but the idea is that if we had any change in soil from one period to the other, it's because of land use change and the amount that you attribute to agriculture versus forestry versus development, which we've acknowledged is a limitation, but also used as a way to say, let's get more soil data, right? Particularly at multiple points in time.
Yeah, and I'd like to add that that's why I wasn't so forthcoming in answering it, because that's my least favorite part about this budget. And that's no reflection on Ivan, of course. It's just the data availability is difficult, but I don't like the way we had to do it in this first round. And so that's a big, we have a little wish list going on the side of what we'd like to put into version 2, and that's pretty much near the top of dealing with a better estimate on what's going on with the soils.
just very quickly on the topic of soil carbon, we had a question from Peter Nelson. Is there, let's see if I get this all, is there any hope of better constraining soil carbon with SAR, et cetera? Meaning, can we better measure soil carbon with some of the new remote sensing products?
No, I don't. I haven't seen that demonstrated, but Peter, you probably know more about that than I do. But typically the soil is either going to come from a real sparse network of actual soil pit measurements, maybe extrapolated by soil type and elevation. So that's where the SAR would come in. I think where I'd like to see it go is eventually into more mechanistic modeling that you can keep track of the more of a systems perspective of the NPP and the inputs to soils and tracking decomposition and all that. That's constrained with field measurements like at Howland and flux tower measurements and things like that. But yeah, remote sensing is always going to be a part of that.
Cool. No,
that was a really nerdy question, but that's expected from Peter.
Jake had a kind of a PS onto that. He said, that's what I was wondering. The forest soil and forest dead biomass values really don't change year over year for forest it stands.
I'm going to disagree again. The dead biomass does if you measure it right because of the disturbances. That's the pulse you'll see after a disturbance. So that we should, and I think we do kind of see some changes in it. But yeah, the soil is tough to detect the changes.
Great, thank you. You guys, this Adam and Dan, this was a huge amount of information to cram into an hour. This is a really, really effective primer on forest carbon in Maine. I really appreciate both of you taking the time to prepare your presentations and share them with us. Also, thanks to Aaron for sharing links, which we are going to share in the follow-up email from this webinar. We'll also share information on SAF credits. I believe this was approved for 1 continuing education credit, category 1 by the Society of American Foresters. So we will follow up probably next week in the follow-up email for this event. Aaron, any final words for the good of the order?
Nope. Thanks, Amanda, and thanks everyone for joining us. Again, please join us next month with Sarah Nelson and Jay Wasson to talk about changing winters. And just a round of applause for both Adam and Dan for sharing.